Hello, in this lecture, let us derive time independent Schrodinger equation. So, this is the Schrodinger equation for particles which are in potentials. The potentials are independent of time. So, when we solve this Schrodinger equation, the eigenstates which we get are stationary states. Stationary states because potential is independent of time. So, we know the time dependent Schrodinger equation, that is I h bar dou t dou psi by dou t is equal to minus h square h cut square by 2m del square phi for three dimension case is v psi. So we have psi of r comma t. Now, as the potential is independent, we can, in this case, we may write it as function of time, and or we can split the wave function into two functions. Um, One is function of time, and the other is function of space. So, f of t and phi of. So, in terms of time and space coordinates. Now, when we derive this psi with respect to time, here we have f of t and phi of r. So, when we do partial differentiation, this will be constant. So, that gives us IH. Now, here straightly df of t by dt. Because f of t is only dependent on time, so we can put total derivative, which is equal to, and in this side we are doing with respect to space coordinates. uh, so basically del square equals dou square by dou x square plus dou square. So partial derivative with respect to x, y and z. In that case, time will be constant. So we write time outside f of t to del square phi of r plus v into psi. So v times f of t and phi of r. Now let's divide the above equation by phi of f of t and phi of r. So by dividing this with f of t, and we get in the denominator f of t. So phi of r and phi of r will be cancelled, and we will remain with df of t by dt, which is equal to minus by 2m. Here also we divided with f of t and phi of r, so we get 1 by phi of times del square phi of r plus, so here f of t and phi of r, when we put in the denominator, we has v. So basically v is function of space, only it is function of space coordinates, that is position, and independent of time. So now if we see this equation on the left hand side, it is totally independent of r. It is independent of r but dependent on time. Whereas on the right hand side, it is independent of time but dependent only on r. Now when we have, sorry, dependent of t, independent of t, and dependent. So basically, this is a function of time, and this is function of position or space coordinates. When two functions are, when two side, it's of an equation or function of two different variables, then this must be equal to a constant, and that constant is energy. So here minus h. So it is obvious that this equals to energy, because if you see the left hand side here, potential energy we have, potential energy plus something. So this term totally is also energy. Energy plus, that is kinetic energy plus potential energy is equal to total energy. So here plus um, del square of phi of r plus equal to E. Now when we take phi of r to the other side, or when we multiply the equation by phi of r, we will get, which is equal to E. Let's call this equation 1. Now from the above we have that IH, from the above we have this, let me, I by f of t, df of t by dt equals to constant E. Now when we rearrange the terms and get the differential equation like this, so E times f of t by IH cross, so basically df by dt is equal to, here we have, or else let me write the final form to solve the differential equation. So hmm, df of t by f of t is equal to 1 by IH cross E dt. Now when we integrate on both sides, integrating on both sides, So um, 0 to f of t, because initial when time t is 0, f of t is also 0. 1 by I h is going from 0 to t edt. So this will give us ln of f of t. In fact, f of t is going from mm, 1 to f of t. When time t is equal to 0, f of t is 1. So ln minus 1 is 0. This will be is equal to e by I h cross times t, because dt is t, and when we take limits so 0 to t, then that we can take t dash instead. So here we get f of t equal to e power just sorry, ln f of t is equal to e by um, 1 by I is nothing but minus I h cross. Here t dash or t minus 0 is t, giving us f of t is equal to e power minus I e by h cross into t. So we are able to solve for f of t in this case. Also here on the right hand side we have energy. So it is basically relating energy to the time. So the equation which we have written above, this equation 1, this is nothing but time independent Schrodinger equation. So also one more thing to note is that we have written psi of r comma t as f of t into f of r. When time t is equal to 0, f of t is 1, but it is never 0. Suppose if f of t is 0, then psi will be equal to 0, which is not a physically realizable system. So f of t rather starts from 1 when time t is equal to 0 to f of t. Always remember
Infinity or 0.
basically if it is 0, that means if psi is 0, basically that is a trivial solution that doesn't represent some system. So it cannot be a solution to the Schrodinger equation. That means psi can also be 0, but psi equal to 0 is not a solution of the Schrodinger equation because it is a trivial solution. So let's look at this Hamiltonian, which had equal to minus h squared square by 2m plus p of. So the time independent Schrodinger equation which we got, we can write. So here basically phi of r into phi of r here. So h cap equal to the above equation, which is equation 1, can be written as this. Now h cap is an operator that gives us the total energy of the particle. Basically, it represents the total energy of the particle, and solutions of this equation are called eigenfunctions. So eigenfunction is nothing but the wave function which is solution to the Schrodinger equation. And our equations are eigenfunctions and corresponding energy values and corresponding energy values of the eigenfunction are called eigenstates. Eigenstates that have eigenvalues. It's called eigenstates, that is energy eigenvalues. So here E represents the total energy of the particle in a given system. Um, Therefore, let's write the time independent Schrodinger equation. So the time independent Schrodinger equation that we obtained, mm, So initially we have written psi of r comma t equal to f of t multiplied with phi of r, and we got for this f of t we got e power minus I e by h cut times t into phi of. So now here what is the probability density for these states? That will be absolute value of psi whole square. So this is and when we calculate, this will be is equal to, so absolute value of this is 1 basically, equal to 1. So probability density of the states will be equal to this, which is depending only on the space coordinates and independent of time. So this is an important thing to note. Probability density, PB for probability density is independent of time for these states. So I will give you the definition of stationary states. So now we are in good position to define the stationary states. The states of a quantum mechanical system for which the probability density does not depend on time. That is, probability density remains constant at all times, are called stationary states. So depending on the potential, that is, if potential is independent of time, then we get stationary states for that quantum mechanical system. Depending on the potential, there could be different number of different solutions based on what the potential is. So like phi 1 r1, sorry, this is not r1, it is r phi 2. So these are m number of solutions um, corresponding with energies E1. These are different eigenstates E1, E2, E3, so on up to En respectively. So we know that the solutions of the Schrodinger equation obeys the principle of superposition, like their properties having a superposition of the solutions. So um, we can write a general state solution as like, so I'm writing the general state solution based on superposition principle of these states. We get a general state solution will be equal to psi of r comma t. So j is ranging from 1 to m in the above case, where we have Cj and e power minus I. So Cj is something a constant. Um, Cj is arbitrary complex constant. So whenever a solution is superposition of other solutions, in that case we can super there is it is related by some constant like Cj, arbitrary complex constant. When we multiply this arbitrary constant to this specific solutions, and then we superpose those solutions, we get general solution. So this is the um, time independent Schrodinger equation and stationary states general solution. Also, the important thing is that stationary states means the probability density is independent of time for these states because potential is independent of time. And we have seen what is eigenfunction. Eigenfunction is the solution of the Schrodinger equation, and corresponding energy values are the energy eigenvalues or eigenstates. So this is all about time independent Schrodinger equation. Thank you so much for watching. Please do subscribe.